So thank you. I want to talk a bit about what we do in our group and what I get excited about. And I think did the usual professor faux pas of trying to put everything in my slide deck. So I hope I get through most of what I want to talk about. But we are really interested in creating interesting aerial robotic systems, both the mechanism and the autonomy stack. And I want to talk a little bit about some of the ideas and how we go about in doing this in my group. I think we live in interesting times, of course, for many reasons, but specifically here, maybe, we're at this sea change in mobility. We have these autonomous cars that are becoming very commonplace. We see these driving around. Those of us in the Bay Area hardly notice them anymore, except getting annoyed that they're blocking the intersection or whatever. But we see these everywhere. We also, maybe a bit farther down the road, but we have these urban air mobility designs or concepts that are, somewhere between, reality and fiction. I should really remove volocopter at this point, I think. But, Whisk and Joby certainly going strong. The Chinese have various interesting concepts as well. And a lot of this, of course, coming through, or a lot of the impetus comes from aerial robotics. And we see, interesting systems that are out there that have very different sort of characteristics. And what I'm interested in is how do we make these systems? How do these systems come to be? What are the design trade-offs? What are the processes that make us choose certain morphologies over other morphologies? And how can we make this easier for the engineers to create interesting systems like this? So when we're creating such systems, we typically, we have trade-offs that we are struggling with. So if you want to build an air taxi, you want to be quiet, you want to be autonomous, and you want to be safe, and often these are in tension with one another. So how do you think about creating the systems, and especially how do you create autonomous systems? So often what we would do as designers is you build a system and then you pass it on to the next person, and the next person tries to make the system autonomous, design the control loop, etc. And what I'm sort of trying to get towards, or at least sort of play with, is how can you simultaneously do mechanical design and controls design sort of in one loop? And especially how do you use, for me, controls theory as a lens towards this? So how do we think about this from a controls theoretic perspective? So my list of slides is long, and what I want to do in my long list of slides, hopefully, is talk about two specific challenges, which are sort of problems, and then in those problems, I want to sort of show three vignettes of different approaches that might solve a particular problem, and then briefly talk about sort of some newer work where we try to close this loop. And these first two sections will be mostly designs that sprung from some sort of place of inspiration from a designer, and what we want to get away from is having this reliance on the designer's creativity, but something that can automate this. I don't really know the culture here, but if you have questions, feel free to interrupt me. That's totally fine from my perspective. So the first problem that's very common when you're dealing with aerial robotics is moving in complex, cluttered environments. And I want to show three sort of approaches to working in cluttered environments, and I sort of loosely think of them as being smarter, being smaller, or the third option, cheating and just sort of redefining your problem so that it's no longer a problem. So sort of first, if you want to be smarter, and this is sort of very robotics-y problem, I have a robot, I want to operate in a complex environment, I want to not collide with the world. How do I go about this? So a very classic approach to doing this as a roboticist is you take your system, you have an inner tight loop that does state estimation and some sort of low-level control. You have an outer loop. This outer loop typically does some sort of mapping and some global planning inside the map, and you then have a stack like this. What's nice about the stack is it's modular, so you can reason about optimality for each component separately, which is good. The downside is it tends to be somewhat fragile, and it's fragile, I think, conceptually because these blocks are connected with narrow connections, right? So the state estimate is a very low-dimensional representation of a complex thing that you're dealing with. The outer loop is also safety critical, so if something goes wrong in your map, you generate a plan in a map that's incorrect and you end up crashing with the world. So one of the things that we've been sort of interested in and working on a few years in my group is to sort of try to put more intelligence in the sort of lowest level control. And specifically, how can we do really fast reactive planning inside this innermost layer? And the idea is now you move a lot of the safety critical aspects from the slow outer loop into this inner loop, and that potentially isolates you from problems in the outer loop, makes you more robust, and gives you hopefully better overall performance as well. And really the idea here is I have rich sensors, I have more compute, so I can put more high frequency computation to do feedback control and planning at this innermost layer, and how can we go about doing this? So I'll talk about this a bit first. The way we do this is we will have our robot, it has some onboard sensing. In our case specifically, we use depth cameras a lot, specifically the Intel depth cameras because they're light, and they give us a very rich information here. So 2D cartoon of our robot that has a depth camera. The depth camera gives you this free space in front of you, and this is sort of, you get these pixels, and then you know there's at least something at the pixel, you don't know what's behind it, so you have this free space that you know is free in front of you. And then what we have is we have an algorithm, which I'm not going to talk a lot about today, for quickly taking a depth image like this, decomposing it into a bunch of pyramids, and then you can do planning inside those pyramids very quickly. And the idea here is this exploits, on the one hand, sort of differential flatness of the drones, and then the geometry of a pyramid allows me to do things like finding routes and detecting free space very quickly. So skipping those details, what we can do is we can very quickly take a depth image and generate possible motion primitives inside this depth image that we can check for collisions. This allows me then to effectively use this depth image as a local map, right, that I know is safe, and if I do planning in that, I should be able to do collision avoidance at this innermost control layer, where I also do things like disturbance rejection. So the way we implement this for our typical projects is we have a drone. It's about 1.4 kilograms. We have an RB5 computer because we had a project with the Army and they said, no NVIDIA's for you, so we're like, fine. We still run ROS1. We have a PX4 that we use, and then we have the Intel depth camera, and we're running OpenVINs for visual inertial odometry, so that's how we do the local state estimation. And initially we thought, okay, with this pipeline, we will really, the limits of performance will be things like the acceleration limits of our system. So here, I'm just going to show you this video. This is a drone. We have our safety pilot at the back, Xiangyu. He is not doing anything relevant at this point. This is the drone flying through this eucalyptus forest we have, where it is doing this onboard planning. And initially I thought really how fast you go will be primarily driven by the depths that you can see and your ability to brake, right? So I know I want to be able to stop before the edge of the world that I can perceive. But very quickly we realized that the problem here, the limit you run into is not dynamics, it is perception. So what happens is the perception system will fail before you hit the dynamics limits. And our planner is very good at planning up to the dynamics limits, but not necessarily good for thinking about the perception. So then in the sense of, trying to be smarter about collision avoidance, we then wanted to create a planning approach that uses perception information in the planning loop. So the idea is when I'm doing motion planning, incorporate in the planning not just dynamics limits, not just obstacle information, but also how this robot will do sensing, and then try to use prediction of how well you can do sensing along trajectory to find good trajectories. And specifically what we do is we have the camera on the robot that's doing visual inertial odometry. So we know what features we are sensing in the environment. These are what we're tracking to do our state estimation. And we're interested in having more features is good, more features, more information, and motion blur is bad, right? So if you have a camera and you sort of move it quickly, you can imagine that the precision with which you can track a feature will go down. So the way we sort of pose the problem is we have a planner. This planner starts with some initial condition. It has a goal position that we want to get to. This goal might be close, it might be far. We want to fly from the start position towards the goal. We want to not collide, of course. We want to somehow have a smooth trajectory. But then also we add this new constraint of wanting to minimize the uncertainty along the path. And specifically, if you have, if you want to start here and there, I have some obstacles I want to avoid. These gray dots conceptually are visual features that I see, and there might be two possible trajectories that avoid this obstacle in different ways. The one likely has more visual information, so we'll have better perception along this motion. So on the one hand, we can do this rapid sampling that we do, and we can evaluate sort of with the known features which candidate or which trajectories see how many features along the motion. But what we also do is we can simulate the camera motion and predict feature motion blur. So this here is just sort of a camera frame with a particular feature, obviously zoomed in at the sort of pixel level, and showing the sort of center of the feature, and as it is smeared out, of course, there will be fuzziness or there will be blur due to just the properties of the camera. But also as the camera is moving, there will be this motion blur. And what's nice about this is the motion blur we can predict fairly well because we know the shutter speed of the camera, and if you know your motion, you know the linear speed as well as the rotational speed, you know the relative location. So I can predict this motion blur, and I can map that into some sort of uncertainty for an EKF maybe down the road. So what we can then do is we have a receding horizon planner. That planner runs, we take a depth image of the world, and then we have a timeout. In this case, we run it at 10 hertz, so not that fast. So 100 milliseconds, where we generate possible motions. We do this with this obstacle avoidance. We can check whether we have collisions doing these pyramids. We can check whether we're input feasible. Each of these motions ends at rest in the known free space, so it's sort of recursively safe, because the worst case, I just stop somewhere and maybe I fly into a tunnel which has a dead end, but I should stop before I see the end anyway. So if the world suddenly becomes unsafe, I have a to-rest safe trajectory. But I can also predict for a particular motion, knowing the visual features that I already see, what will be my accumulated uncertainty during this motion. And what we now do is we have two orthogonal objectives. One is fly fast, and the other one is have good perception. We do a relatively naive convex combination of these two to score each motion, and then we just keep the best one of these as we're sampling. What's nice about this is it gives you something that's recursively safe in the sense that every time you run out of time and you select something, it is known to stop in the safe space, right? So worst case, you'll just end somewhere with no plan, but you should never sort of end in a situation where you crash into the world, as long as you perceive the world accurately with the depth camera. So what's nice about this is this gives us sort of cool behavior. So this is our baseline planner. This will be a drone taking off. We're tasking it to fly 30 meters down the road. This image at the left here is the depth camera, and on the bottom is the monocular camera we're using for feature tracking. Annoyingly, I marked the feature in blue, which is basically invisible on any projector, but you can see the features on here. And if I play the video, what you'll see is if all I want to do is fly quickly, the drone flies in, as you would expect, more or less a straight line down this road. It's not a perfectly straight line because we have these random samples, so there's a little bit of just randomness in that motion. But this would be, all I care about is speed. Now, if I now add this perception-aware component to it, what matters is if you look at this on the road, there's very little visual contrast. So what the system will do is, again, tasked with just flying down or flying down range 30 meters, it will actually veer towards the left-hand side where there's just more visual information, right? So it has, it trades off some of the speed for being more confident in its motion and flying closer to these visual features, which then give it a much better understanding of where it is. What this gives us, and this is a very busy graph, which I apologize for not really spending as much time on as I probably should, but what we can do is we can take these flights and we can show that the uncertainty or the EKF variance, so effectively the uncertainty as you're moving, is reduced. Anecdotally, we find that these fragile failures in the perception system disappear the way we've set it up. Certainly we're conservative enough that they don't seem to be happening. I can't prove that because these are sort of fragile sudden failures, but with the baseline we do have this where it's fine, it's fine, it's fine, suddenly it's very wrong. With this perception aware planner we are much more robust, and we can sort of at least numerically show that the number of features we track is higher when we have the perception aware planner. So specifically without the perception aware planner, there's sort of regions where there's very few features, but if it plans with that in mind, we have sort of more features, and also the uncertainty then is lower. So this is one way to try and be smarter. Another thing you can do is sort of try to change your shape relative to the world. So we like interesting mechanics in my group. So one of the interesting mechanics was inspired by one of our integrative biologists who told me their birds were better than our robots. And of course, birds are really impressive. So this is a goshawk flying through a narrow environment, and we see it changes its shape as it's doing this. Here's a totally gratuitous slow motion of the same sort of behavior. And we see that the way it does this is it has these internal degrees of freedom that it can manipulate to effectively make the world seem bigger. So we were inspired to try and make a drone that has something similar. So we wanted the ability to shapeshift. We don't want additional actuators, so we're going to rely only on the actuators that the drone has already, which are the 4 motors. Ideally have the ability to shapeshift, but retain what makes a quadcopter good, which is the simplicity. The way we ended up doing this, the second iteration, the nicer design looks like this. We have 4 arms. Each of these arms has at the end a thruster, the propeller. It has a sort of hinge that allows it to fold 90 degrees up or down. There's a mechanical stop on each end of this. The propellers are bidirectional, so you can imagine if you anchored the body and the propeller pushes up, you'll extend. If you reverse thrust, you'll push down. In flight, it's a bit more complicated than that because there is no anchoring, but fundamentally I can then have all 4 motors deployed straight and then fly like a quadcopter, or I can reverse the thrust on some of these and fold them down. And this gives us a system with sort of interesting capabilities. So here we see the drone take off, fly like a quadcopter, and then fly through this narrow tunnel in this shape-shifted configuration. And then transition back. And you notice there's, maybe jump back, apologies. The way that the hinges fold is not quite aligned, and this is so that you still have yaw authority, which gives us the ability to hover the system in this reverse configuration. It is horrendously inefficient in the folded configuration, like you wouldn't want to do this for a long time. On the one hand, obviously, just because the disk area is much smaller, so half the size, so that's going to be much higher power configuration. But also the yaw torque is actually quite high that you need, and the propellers are very inefficient in reverse. But you can do things like do these flights. You can also do other things, like we can do some very limited manipulation. So full disclosure, the box has to be empty because we don't have enough grip nor thrust to carry anything bigger. This is obviously not the design point. We just discovered this sort of by accident. But you can use this mechanism for other interesting things. So you can use this to say pick up this box and then you notice our position control is not nearly as good when we're carrying the box, but then do some very limited manipulation. You can also do, and where's Dan if he's here, you can do some sort of perching with this as well. So if you land on a wire, and I sadly don't have a video, the 4 arms fall down and that moves the center of mass below the contact point, so you have a sort of very natural perching behavior. It does come at some slight cost, so there is some control logic that you want to be careful about thrust limits so you don't accidentally fold the system, but that effectively just moves your minimum thrust up slightly. Okay, so that's morphing, and then the third thing to operate in dense environment is to cheat and just sort of embrace collisions. So here we were interested, and this was inspired by the DARPA Subterranean Challenge, in creating systems that can really just operate without any sort of knowledge of the environment, so no interest in avoiding collisions necessarily. This is a tensegrity shape, and I was very happy to see there's a tensegrity sculpture just outside here. So tensegrity shape is something where you have some rigid rods that are enmeshed in a series of tension elements. What's nice about these structures as an engineer, as a sculptor, they just look cool, but as an engineer here, what's nice about these is if you apply an external load, it is distributed internally either as tension in the strings or as compression in the bars, and both of these can be very strong modes. This is as opposed to if you think of sort of a classical quadcopter maybe with an arm, if you hit the end of the arm, there's a big bending moment at the shoulder, which is where you would have a failure then. So what we did is we built a quadcopter in a 6-part tensegrity that then allows us to do very large collisions. So we don't need to know anything about the world. We can just sort of crash our way through it. To design this, there's all sorts of analysis. This was sort of a cartoon FEM system we created that we could do collisions and sort of try to understand just how the forces would be distributed to size the robot. But the end result is a system that looks like this. This is a robot on Berkeley campus. We're not allowed to fly, so this is hopping for the lawyers. So this is the robot. Its task is to just move forward. It has no external sensors. It just has its IMU. And its task is to move forward through the world. And it has no information that it's on a ledge. So what you'll see here is the robot take off, and then it falls down because it doesn't know where the ground is. It is approximately spherical, so we can use the motor thrusts to orient ourselves more or less upright, and then we can keep moving. So we've bashed this thing into our lab concrete wall at like 7 meters per second is fairly reliable. 10 meters per second you can do a few times, and then eventually something will break. But it's a very robust system. And what you can also do is you can do motion. This is a robot tasked with moving from this side of the tree to the other side of the tree, again, it's only using its accelerometer and rate gyroscope. It has no information about the world, and what we'll see is it'll crash into the tree. Of course, we can detect a collision with the accelerometer, and we do these hops. The reason we do the hops is this allows us to do dead reckoning with a fair amount of precision using only the IMU. The logic here is very simple. If you collide with something, hop to the left a meter and then try to go back to where you want it to go. But I want to just sort of show here, it's kind of impressive that you can get pretty good dead reckoning from this. And the key here really is the hopping. So this is a zero velocity update. Was at least I got this idea from people who were doing foot tracking with IMUs when you do footfall. And the idea is when you know you're stationary, you can do a Kalman update with zero velocity. And this really sort of shrinks that dead reckoning error from t to the 5 to in the order of t. Okay, so that's cheating to solve the problem, I think. Another problem that we always have with aerial robots, I'm going to go fairly quickly through these, is just how can we be more efficient? So how can we reduce energy requirement or use the energy we have more cleverly? So again, there's sort of 3 projects that have played with this idea, sort of much the same way. One is, can I be smarter, right? So can I adapt my trajectories to use my energy better? And then some morphing, and then cheating the problem, sort of just going around. So power consumption of these systems is very complex. If we think about a typical battery electric aerial robot, you have the battery that takes chemical energy, turns it into direct current. You have the speed controllers that take the direct current, turn it into alternating current, that then drive the misnamed brushless DC motors that spin a propeller that pushes the air around that causes me to fly. Now, I am not particularly interested in the first few things. These you pick from a catalog, you do a good job, hopefully, and then you get fairly good performance. We were sort of playing with the last bit here, right, is where the propellers meet the air and how we can think about efficiency here. And in general, this is difficult to model well. So the propeller efficiency is a complex function of speed of the propeller, like motion, translational speed. The aerodynamics of my system is complex, drag of the body, drag of a payload, etc. And the system before this is actually also a fairly complex dependency on the rest of this. So the electrical consumption will depend on the speed, the set point that I'm running at, which will vary if I fly faster and I have to counteract drag, things like this. So after trying and failing to do anything model-based and predictive, we kind of gave up and tried just sort of a purely data-driven approach to more efficient trajectories. The intuition was, I have a system, I want to fly from point A to point B, so I assume that I have a reference path that I want to follow. And if I fly faster along this reference path, I will have higher drag, right? So just bluff body drag will go quadratically in speed. But at least to some extent, the propellers will be more efficient. So as I move faster, I can have some more efficiency. Juan is going to murder me if I say this, but because the air is cleaner if you fly into it. And what I get to vary is I get to vary how fast I fly, and I also have this conceptual degree of freedom, at least for these hover-capable systems, of rotating around the thrust direction. So we're going to call that side slip, which is the sort of the angle of your body fixed x-axis with the wind, the relative wind. So you have 2 things that you can vary as you fly this path. You can vary how fast you're flying, and you can vary your rotation around the yaw angle. And this will be very hard to model accurately. So what we did instead is we used extremum seeking control, which is a very old technology from the 1930s, for doing arbitrary functional optimization for a closed loop system. And the idea is using this, we can online adapt to both the speed and the yaw. I could talk too much about the mechanism. The intuition, for those that have not done extremum seeking control, is that you have an input signal, you overlay a sine wave on that input signal, you look at the output signal, that will have a sine wave with the same frequency, and then with a convolution of these, you can effectively get a gradient, and you can walk down the gradient to move your set point to where you're minimizing whatever your cost function is. We did some work to try and make this faster, because there are these 2 degrees of freedom that you want to optimize, and they're orthogonal and so on, which allowed us to do this quicker. But what this gets you is this gets you a system where we have here a drone flying in our outdoor space. So this is flying a large circle in lieu of a straight line, so we don't need to worry about line of sight. But this drone is flying this large circle. We have a graph here that's the forward speed at the top, then the side slip angle, so the 2 degrees of freedom that we get to vary. There is the energetic cost per unit distance so joules per meter. And then the bottom is just the local wind as we measure it from a base station on the ground. And what we see here is the speed and the side slip. These dotted lines are things that we just did some offline characterization, and these are approximately where we think the optimal are, but they do converge to this. And what's nice about this is this allows me to really converge with no other information. I don't need to know anything about the payload. If you give me a different payload today than yesterday, this should also be able to converge. Then, as I said, we were worried about speed, so we did some adaptation, so modification of this algorithm specifically. We, as researchers in the 21st century, have done a lot of work on stochastic optimization. So some of those ideas you can apply to extreme seeking controller to just make it converge faster. So we sort of played around with that. But the details are probably not so important here. But again, this is sort of just being smarter, right? So taking your system and just sort of playing with the algorithms to get more out of the system. Then again, my heart beats for weird mechanisms. We made a weird mechanism for morphing the system. So if you take a drone, a quadcopter, and you try to fly at high speed, you end up with something that looks like this. So this is very cartoon level CFD. But you have the drone, you have to produce your thrust forward, and then you have the drag of the system that you need to overcome. As you try to fly faster, you basically increasing that surface area, so you have more drag, which means that you have much less efficiency. And ironically, the system tends to act like a wing pointing downwards, so you actually have negative lift that you also need to compensate. So if I could tilt the propellers without tilting the body, right, I could sort of get the forward thrust without this additional drag. So we worked on a system where I can tilt the propellers, but again, do this without actuation. So I only want to use the 4 motors. The 4 motors I have to have anyway, but get the system that can operate in these 2 different configurations. The way we did this is with a sprung mechanism where we have all 4 of the propellers are, so there's 1 internal degree of freedom, so they all move together. There is an internal hinge and a spring attaching the propeller to the body. And what happens is, you can think of it as sort of a click-click bistable mechanism where in the downward configuration, there is a certain maximum amount of thrust where you would overcome the spring's restoring force. You would have this thing buckle up. It will hit some mechanical stop. When it moves, the spring's geometry changes, so that restoring force changes. And then to get it to go back, you need a much lower minimum force. So what this gives us is this graph here shows with the 2 configurations, so tilted forward versus perpendicular untilted configuration, the thrust I can produce without tilting. So if I'm in the untilted configuration, I can produce up to 0 thrust, of course, and then there's a maximum thrust beyond which this thing will tilt. Once I have reached the tilted configuration, I have the top range of feasible thrust forces, and if I exceed this minimum force, then I will sort of tilt or switch back to the original configuration. And what's nice about this is we can hover in either configuration. So the blue solid line here is the hover thrust, so you can have this vehicle hover in either configuration. What does this look like? This is the vehicle flying outdoors. Doing that switch here is in our lab, doing this switch. Of course, not particularly useful if all you're trying to do is hover. Maybe just by motivation. The untilted configuration is nice. Why not always tilt? The untilted configuration is good because you have larger moment arms. So at low speeds, you are more maneuverable with perpendicular propellers, but of course, you just have higher drag. But what this gives us is much higher maximum speed, for example. So here we have the system with the tilted configuration on the right and the untilted configuration on the left. And we can achieve sort of a 12% faster flight. I forget what the efficiency number is at the same speed. You can also show something like 10-15% decrease in energy that you require while flying. Again, it's not quite for free because there is some thrust limit you have now. So when you are flying, you have to plan a little bit about, say, maximum thrust or minimum thrust so you don't accidentally switch configuration between these 2 configurations. And then lastly, on this topic of efficiency, how can we cheat the problem? So again, I want to fly a long time. Let's just think about changing the problem so that this is easy to do. So if you think about this powertrain that I've described, if you think about how the propellers interact with the air, a simple model of this is what's called the actuator disk model. This is almost cartoonishly naive. When you first learn about it, you model the propeller as sort of this magic disk that just adds energy to the flow. Nothing is rotating, but it's surprisingly predictive. And if you do the math for this, you come up with this power relationship. So the power that I require for a propeller will be proportional to the force to the power 1.5 and inversely proportional to the radius of the propeller. This is for a stationary propeller, but this gives me sort of a predictive thing if you want to sort of guesstimate how will power requirement change if you change the mass, or if you change the size. This gives you sort of some idea of how to do this. And from this, of course, you learn that, okay, if I want to do long duration flights, I either want to have a lot of energy or low power. I can reduce the power by increasing the size of the propellers or reducing the amount of force I need per propeller. I can also, of course, change the amount of energy I store. So this graph here says, okay, let's take a drone, say it has unit mass without battery, and then change the amount of battery that I carry. So cartoonishly, I'm going to allow it to carry an arbitrary amount of battery. So on the x-axis, we see the battery or the total mass with unit 1 mass, meaning 0 additional battery, and then more and more battery. And on the y-axis, we have the flight time that this thing can fly. And of course, if I have no battery, I can't fly. Not surprising. As I have more and more battery, I can fly longer and longer. And then there's some maximum beyond which adding more energy to your system actually costs you flight time. Why is this? Well, loosely because batteries don't get lighter as you deplete them. So at some point, the cost of carrying that additional energy, you have to carry it empty all the time. That ends up costing you more than it gains. So there's some fundamental limit to how long you can fly, no matter how efficiently you design your system. And that's unless you cheat. So the way we cheated is with what we called flying batteries. So the idea is I have my main system that I want to have do something useful, and then I have a small system that just brings it more energy, right? And what this gives me is it gives me a robot that can fly potentially arbitrarily long. So I'm going to show you here a video where we flew for around 80 minutes. It's not 80 minutes long though, where we can have this main unit fly. It has itself a fairly low mass, right? It only has enough energy for effectively taking off and landing, but we can bring additional energy to it from outside. And the way we do this is with these smaller systems that are obviously carrying a much larger battery than they themselves need. And then, up here, there's some circuitry to make sure you don't set fire to the drone and so on as it's, you connect these batteries. The circuitry is not that sophisticated. It's effectively some diodes, which just mean one-way current flow. But here you see this maneuver where we then have the battery come in and out. And what we can now do is we can fly effectively indefinitely with the main system. And if you're doing something like an air taxi, this might be one way to get around the problem of how do I make a system that is light enough and small enough that it can land safely in crowded environments, but still have useful range. Well, just bring the range as you're moving, right? So you don't need to carry everything with you. Yes, okay. You can imagine, of course, doing this, there's all sorts of complexity here in this maneuver and the mutual interaction, which I'm not going to get into. We've most recently been sort of playing with using learning control for doing this docking maneuver, which seems like a lot of learning to work surprisingly well with fairly little effort compared to originally when we were doing a lot of model-based feed-forward type corrections for the aerodynamic disturbance. So with all of this, how do we go about automating this design process? So each of these problems, what I've shown you, these three different, these different approaches effectively come from some spark of inspiration, right? So you have some idea of, why don't we try folding the arms or something like this? And how do I automate this problem? So how do I go about giving a designer a tool where maybe you do more of a high-level sketch of the problem and it then gives you some possible designs? And I think we'll never get to the point of automatic design because at the end of the day, the design space is always too complex and our value functions are always too vague that you can never meaningfully automate the whole system. But what I'd like to have is I'd like something that, gives me a rough idea that's in the feasible space that is then for me to interrogate, right? So then I can take this and sort of play with it and see how well it might fit my particular problem. So I want to talk about 3 ideas, depending on time, about how, that sort of plays with this. Now, we've done nothing in terms of solving the actual problem, but sort of that go in this direction. The first will be on sort of designing a closed loop or doing closed loop co-design, then learning from simulation, and lastly, sort of synthesizing interpretable policies, which, if you'll humor me, hopefully fit into this bigger problem. Okay, so the closed loop co-design is motivated by a fairly mundane material handling problem. So maybe I'm on a construction site, I want to carry some sort of oddly shaped material from one point to another on this site. I'm going to assume I have access to a bunch of lifting units, drones, effectively, that I can somehow attach to the material I want to carry, and then I want these things to bring my material somewhere that I want to go. And, of course, these are drones, so I can't replace the crane because I can't pick up really heavy things, but I can potentially help by moving some lighter things from point A to point B. Now, if I am doing this, we're going to assume that the payload I'm moving, I know its characteristics. So I know the geometry of the payload, I know its mass characteristics, and I am able to attach my lifting units somewhere on the perimeter of the object. And what I'm going to search then for is where should I attach these lifting units on this object so that I have robust performance, right? So robust performance for us, I'll define in a second, but just loosely, if I am there, I want to carry this particular weird box, where should I put these things so it gets there even when there are disturbances? It's sort of a cartoon of a drone design problem where the only thing I have, the degrees of freedom I'm playing with, is the location, and I'm doing this on a 1D search for each agent, so it's a very simplified controls problem. But I want to do this in closed loop, so I want to know not just, I don't want to design some open loop characteristics, I want to have something that tells me, for the best controller, this is the best performance you're going to get. Our control objective we frame as follows. So we say that a robust system will be one that has least probability of actuator saturation. So you can imagine as there are disturbances, your thrust forces will vary, and I want to keep those thrust forces as far away as possible, or I want to reduce the likelihood of them hitting either the minimum or the maximum bound. The thrust force I have in closed loop, of course, consists of two things. There's the static feed forward term, right? Just sort of the hover thrust that I require to keep this thing flying. And then there's the feedback term, which is in response to disturbances. So what we do is we model our system and we linearize it, and we assume that the disturbances are Gaussian. The disturbances here are force and torque disturbances acting on the system. And then we do an H2 approach to effectively calculate the statistics of the inputs. Then we calculate this Mahalanobis distance, which is a bit of a kludge, to approximate the amount of probability mass that we have within the feasible range. So we're not actually solving the problem. Notice how I'm sort of breaking it into approximations. But using this, we can then calculate for certain configurations, at least with this Mahalanobis distance, what is the smallest number of standard deviations in the multidimensional sense that I am away from a saturation of my actuators. And then as you have different designs, you can then calculate this. This is fairly cheap to calculate. It's not milliseconds, but we can solve this in seconds for a configuration. And we don't, it's offline, so you're not doing this in flight, right? So seconds is fine, but we've not optimized it beyond that. You can then figure out where is the optimal configuration. So the end result then, I want to show you two videos. First, this video, the payload we're carrying is I should point with the mouse for those online. The first video, the first payload is a very boring square. And if I asked you to attach the 4 lifting agents to a square, you'd probably come up with the optimal configuration, which is put them in the corner. This video is just supposed to show, we predict some difference in performance, and we can measure that difference in performance as well. So the optimal configuration does actually outperform the suboptimal configuration, even when it's, in this case, probably not particularly useful to have heavy machine to solve this problem. But we also had this payload here, which I think is more interesting. So this payload, it looks more or less like an M. We are going to attach 3 agents to it. If you had asked me, I would have guessed this configuration on the right, sort of the symmetric configuration. But if you run our tool, it spits out the configuration on the left. It is a locally optimal configuration. This problem certainly is not convex. You can imagine certainly you have permutation, so there's no unique solution anyway. But this is a locally optimal solution that is more robust. And we can sort of then do experiments and see that. So here, we have these things hovering, and what we're doing is we're adding a payload disturbance to it. And you can just sort of see how much better the system responds to that. And again, the idea is when I'm posing the problem, it gives me not only the mechanical layout, but implicitly through the H2 control analysis, it also gives me the feedback controller gain, right, that you should fly with this. Okay, so that's one thing, and this we can do for simple problems where we can linearize and use all of these great tools from linear control. If you want to go beyond this, it's hard, right? So for systems where we do complex maneuvers where the nonlinearity matters, I don't know how we would go or we solve these kinds of problems except very large-scale Monte Carlo, which would be slow. So one of the things that's not quite in the design space yet, but is just if you give me a weird design, can I come up with a good controller for it without the designer having to sit down and do that controls design? And of course, a lot of our learning techniques go to this. So I gave Daisy, the student that worked on this particular subproblem, the challenge of just design a controller that will carry different payloads smoothly. Like, I don't want to tell you what the masses are, just adapt to different payloads as you're flying. But then we quickly realized that that's pretty easy, and we pushed this, and the cartoon problem now is design me a controller that can fly any quadcopter. So give me a little chip, that I can hot glue onto your drone, attach the motors to it, and it'll fly. I do need to know that the motors are symmetric, so it's not it looks like an X. And I need to know which direction is forward and what the IDs of the motor are, but I don't need to know the size of the system. I don't need to know any mass properties. I don't need to know the speeds of the motors. I am just giving the motors some sort of black box command, and I have access to IMU data and my actions, right? And from this, I want to fly this quadcopter. We do this in simulation. We train the system, and then we deploy something in experiment. And I want to briefly describe how we do this. The idea is to create this low-level controller that effectively commands the motors and tracks some high-level controller commands. The idea is if I can do this, I know how to do motion planning for quadcopters. That's easy. If I have this controller, it'll hide the physics of the drone from me, right? So I, as the motion planner, I don't need to know things about mass properties. This controller will take care of it. I just need to do high-level trajectory design. Of course, what's fun about this for me is this is a controller that's very much safety critical and high bandwidth, right? It's the innermost thing. So if you screw this up, your system will not fly. So the way we work is we have some sort of outer loop that sets some desired position. We have a high-level controller. This is not particularly interesting here. It's just our lab standard nonlinear proportional derivative style high-level control. And then we have this innermost neural net that does the tracking and hides the physics. We learn this controller. We base this off of the RMA architecture that I think especially was popularized by Jitendra Malik, this group, when they were doing legged robots. The idea is you have something that looks a lot like indirect adaptive control, where you have a low-level controller that has as input some sort of parameters that are a function of observations. So your low-level controller is in the indirect adaptive control, typically an LQR controller that's parameterized by, say, mass parameters, and you have an extended Kalman filter which estimates the mass parameters as you're operating. Here, none of this is model-based. It's all black box neural nets. So we have our low-level controller. We have what we call an extrinsics encoder. The extrinsics encoder is trained in two phases. In the first phase in simulation, we train a low-level controller that is parameterized by these extrinsics. The extrinsics come from an extrinsics encoder that in the first phase have access to the true parameters in simulation. So the true mass parameters, the true size parameters, the true propeller coefficients, things like this. In the second phase, we freeze the low-level controller and we just learn an adaptation module that now has access only to the sensor and commands from the system. So, something that you can actually causally implement. Then you learn this to generate extrinsics, which make the system work well. And then you deploy these statically in experiment. When we train this over a fairly broad range. I think these numbers actually I should update since the newer publication was just accepted. But, we train this on simulated systems with mass varying by, almost factor 10, in mass moments of inertia, 2 orders of magnitude variations, things like this. And then we deployed an experiment, and unfortunately I only have 2 sort of typical robots that work well in our lab. So here is just a boring video of these 2 drones flying left and right using this controller. These are not particularly present in the training data, but of course they fit in that range in which we were training. But we see here these 2 systems fly stably back and forth. And what's nice about this is you can really mess with the system. So here, what we're going to do is we're going to have the system flying. This is a slightly different drone. It's going to fly, and what Jerry is going to do with his, you can see how much glee he gets from messing with the drone. He's going to add a large payload as it is trying to fly the circle. At the top is the learning controller. At the bottom is our lab standard controller with an integral term just to eventually get rid of the that mass offset. And we notice how the learning controller, it's to me, it was shockingly robust to these perturbations, right? So it adapts very quickly. It is very robust. If you were to just hover, our lab's model-based controller that's tuned for the system will do better than the learning controller in terms of like RMSE and noise rejection. But for these sort of adaptation, it is pretty incredible. I shouldn't say that strongly. Obviously, I love my own children, and I think my research is incredible. But I was really shocked at how well the learning worked for this. What this video is going to show you is this is the drone being tasked to take off. So it's starting like, it has no information. We messed with the system. What we did is we took the front propeller and we induced a fault by just reducing its effectiveness by 20%. We do this in software. So whatever command the controller gives, we just reduce that by 20%. And on the left, again, the learning based, on the left, the lab's standard controller fails. On the right is this learning-based controller, which takes off. The takeoff is not particularly smooth, right? But then it very quickly sort of catches this and can fly the system pretty robustly to actually hover. And why this is interesting to me is this sort of gives me this idea of if I now want to create a weird vehicle, maybe all I need to do is like zip tie it together, put this controller on it, and I can see how it works. Now, this controller is probably not the best controller. If you sat down and you measured the parameters, you'd probably come up with something better, but it's a reasonable controller, right? So it gives you some idea of what's possible with your system. So again, as a designer, if you want to iterate on ideas, this might be a way of being able to do that faster, right? So evaluating your ideas more straightforward. The last thing playing with this design is the most out there. This is something we're going to present at ACC this year. Someone told me there's a lot of money in large language models, so we thought, good, we're going to do some large language models as well. So far, no money yet, but anyway, we have large language models. So, of course, when you're designing a controller, effectively what you're doing at the end is writing code, right? So the controller is some code, and the code you deploy on your system, and hopefully you get good behavior. So, okay, if I think of my policy as a piece of Python code, can I use these large language models to effectively generate good controllers? What we did is we want to do this in design time. So the large language model is not in the control loop. It is in the design loop. And then you generate some Python code, and this Python code is then used at deployment time. So the code is static. There's no LLM in the control loop. And the hope is that if you do this, you end up with Python code that you can read and modify, right? So it's, of course, the process is some complicated black box, but the end result is something that I can then modify. And the cartoon here is do a genetic algorithm over the space of Python code, right, where your genome in the genetic algorithm is the Python code, and you use a large language model for the crossover, right? So when you take two genes and you want to sort of produce the child, you use a large language model for this. We're only able to do very much cartoon problems with this at the moment, but you can get it to work. Training time here is like tens of hours to end up with controlling an inverted pendulum. So this is the classic inverted pendulum. This is a system where you have bounded torque, and your objective is control it to the upright configuration. We tell the system that it's an inverted pendulum, so it probably, there's some amount of, in the GitHub repos that it's trained on, it kind of knows to look, and sorry, down here is the code that it's actually running. This is the end result. We tell it the input is a two-dimensional array, and then we tell it roughly what the meaning of these are in the config, but it then comes up with some code that is, that is actually legible. You can parse this and you can make sense of what this thing is doing. In training, of course, it is simulating these, and that's how you generate the fitness that goes with each gene. So you hopefully end up with something that works, and then you as the engineer can read this and modify it. Now, the inverted pendulum is kind of trivial, slightly, it's still cartoon simulation, but a slightly more interesting problem is the ball and cup. So the idea here is move the cup so that the ball falls into the cup. Do the same thing. So we train this. This is the output that we get. Again, these are tens of hours on a single GPU just in our lab. And it doesn't work particularly well. So this is a policy which has something like an 80% success rate. You can sort of see it fudging around here, and it's trying to get the ball to come in. On the left here is the code that it generates. It's not particularly easy to read, but fine, there's some input, and there's some if statements, and from this it figures out. What we can do as engineers, of course, we know that some of these if statements are impossible, like if the input is bigger than 5, but also less than -3, right, then do so. So you could prune some of this, but that's not what's interesting for me here. What's interesting for me is I notice the cases where it fails tend to be when it sort of gets stuck in the top right. So I just add some lines of code to this. And here, if I am to the right, then just move to the left slightly. And what happens now is we get to sort of move the success rate from 80% to like 99-something%. We're still only able to solve these cartoon problems. It's still very expensive. I don't think we don't know how to scale this to big problems, etc. But the idea is if you can describe a problem, maybe like this, I can give you a controller, right? It might not be the best controller, but like you as an engineer, you can take this controller and try to make sense of it and modify it to your needs. give me 1 sec because I'm basically done, and then I'll get your question. Before I take the question, just, I get to come here and give talks in front of great people like you and show all of these videos, but of course the students do the hard work here, so I just want to acknowledge the great team I have, the students that work on this, that make all of this possible. Also our funding, of course, will pay for us to play with these systems. And in conclusion, I think what I get excited about is, system design as control design, using control as a lens to think about these problems. The other thing I always try to think about is how can I cheat with physics? How can I take the dynamics of my system to make something that is hard less hard by sort of being creative in how you interpret what your degrees of freedom are. And especially if you think of the mechanical design as part of your, not just the controls gain, not just the algorithms, but the mechanical design as well, you just have more knobs that you can play with, right? There's more space for you to design your system, which potentially gives you better solutions. Good, but with that, I think you had a question. So thank you very much. Thank you.
Yeah, nice talk. On the LLM part, I was curious if the LLM is just doing this genomic combination, or is it actually using any of its reasoning capability as well? Because, the case that you mentioned where, you have some impossible logical cases, right? I feel like an LLM would be pretty good at just reasoning about that and, getting rid of those things.
Yeah, I apologize. I thought I would have less time. So I didn't put the details here. The way we do this is, you can think of it as a standard genetic algorithm. So typically when we do a genetic algorithm, you have a finite dimensional search space, and you have maybe 10 dimensions that you're searching over. Each of these is a real number. You have some cost function that you can evaluate at that thing, and then you have a process by which you take 2 possible values and you generate a child from them, typically a simple average or something like this, and then you evaluate these. And in this way, you can then sort of search through your high dimensional space. The space of code is, of course, somehow infinite dimensional, so you can't do naively like this. So what we do is, the cost function evaluation is you give me the controller and I just run it in my simulation. I see if you succeed or not. What we do with the LLM is we tell it, sort of at least in broad strokes, this is the problem you're trying to solve. These are the inputs, that's the output. Here are 2 programs that solve this problem. Generate a new program that is better. And better is, I don't know. What does any of this mean at the end of the day? It's a statistical model that has no understanding of anything. But what it does, and then there's the hyperparameter of the temperature of the LLM, like how much randomness does it add. But in this way, then you get a derivative of these 2 pieces of information. And then the evaluation is, again, just done in simulation. So the LLM is given the 2 genes and is told, mix them to a better offspring. But what that means is up in the cloud. Now you can imagine here we have these impossible test cases. On the one hand, I'm sure if we asked it to make sure the program is minimal somehow, it would probably do some of that. But also we are just using StarCoder 2, which is just, easy to run locally. If we had deployed this in, ChatGPT is much better coding than what we have, right? You probably have gotten better code. I don't know if it would have made a big difference conceptually, though, in terms of, how well does this work on a real problem? I don't know how to answer that yet because we've only solved toy problems.
And then follow-up question, are you using any sort of curriculum for this? Because I think you're still basically going to situations where you can't get anywhere, especially for more complicated problems.
Yeah, so at the moment we just give it blank code at the start. A big question we don't have a good answer to is what is the function you're evaluating? So what we're doing is we're just evaluating, I forget what the number is, 10 initial conditions, the same initial conditions for all of them. That at least makes it deterministic, the evaluation, but it's not particularly robust, right? So it might end up, what I don't want this to end up being an open loop trajectory that just works for the particular initial condition you gave me, right? I want this to be a feedback policy. So the challenge is trying to set that up, and we don't know how to do that particularly well yet. Okay. So I would describe this as very much early work that we haven't thought through completely yet.
A comment more than a question. Just like a fun thing, I liked your optimization of the drone positions around the object that you're moving, because it ends up being almost exactly the same as a grasping problem.
Interesting.
Uncertainty method is exactly the same as
Interesting. Here you can see my naivety about grasping. It always seemed too hard of a problem, so I've Yes. So this is work with Carlo.
Yeah, so I have a follow-up also about that work. In the second example where you show you use 3 drones to lift a non-square shape, the solution, the algorithm found is quite unintuitive, right? It's not symmetric. Do you have any explanation or a physical intuition behind it? Like why is that solution better? Just curious.
Yes, by which I mean not really. So I think it has to do with where the center of mass is and how the inertias are. So here, the center of mass is somewhere over here, right? Because you're removing this piece. So somehow, if you have these 2 agents, they're much farther from the center of mass than the third one, right? So I think that's, in this configuration, everyone is in the open loop sense. The open loop forces will be smaller. It's some complex, not a complex combination, but it's a combination of the open loop and the closed loop. And I think both of those will be more favorable, like both the controllability aspect as well as the open loop forces will be better in this configuration than in the right-hand configuration.
One of the early works you were talking about generating trajectories that you're sure that you can stop by the time you hit an obstacle. And I think there's a common in a lot of robotics problems, whether it's like a small robot on the ground, so you make this assumption that you can stop. But I'm wondering when you're considering higher level co-design for aerial systems, so I'm thinking like a fixed wing system or even a car on the highway, where just immediately stopping is maybe not a feasible solution if you consider this co-design problem in that space. So like, would you consider safe trajectory being a deviation trajectory or something like that?
Yeah, so that's an interesting question. If you have a system where one of 2 things, either stopping is not an option, like if you have a fixed-wing aircraft and I stop, I follow the sky, so that doesn't work, or where stopping is not safe. So if I'm driving on the highway, stopping is dangerous, right? I think the question to ask then is what is safe, right? So for us, we want to have the property that, recursive safety, if I start from a safe condition, I remain safe, right? At least under assumption. So for us, we assume certainly that you can track the trajectory fairly well, that your perception system perceives the obstacles, that the world isn't moving, things like this. But at least under those conditions, as long as I start safe, I should remain safe during my motion. Now, if I'm on the highway, fundamentally, if the highway is allowed to terminate in a wall, right, it's not clear what I would, how would I even pose that as a problem where safety matters, right? Because clearly stopping is not safe, but continuing is also not safe. So, you need to think about your problem. What would you do? Now, for our system, stopping is an option, and it's a safe option, so that's why we fall back to that. But I think it's an interesting system question for maybe a fixed-wing aircraft. When you're doing motion planning, how would you think of safety? And safety might be, is there enough space for me to turn around? So if I knew it's safe behind me, can I turn back? Or maybe, if I end up flying into a tunnel, that's maybe okay and I'm screwed, right? It depends, I think, on what your problem is.
Thank you. One more question? Yeah. In the example of making the robot smarter, how do you offset the risk of the obstacles when you're taking in more features in the environment?
Yes, so the features here,
Page 17.
something like this, right?
17.
Yeah, so let me just stick to this cartoon here. What we do is we assume that we have, so this depth image, we assume that it's pristine, right? So there's no uncertainty in the depth image. We assume the world is stationary, and we take our robots and we model it as a sphere, which is the size of the robot plus a little bit of safety bound. And it is then a necessary condition that your motion plan as the sphere does not collide with anything in this assumed perfect depth map of the world. So then the trade-off that you do is speed towards the goal. So how much progress do I make versus the uncertainty that you accumulate as you move. Okay, but for both of those, collision-free is a necessary condition before you'd even consider the cost. I don't know how much time we have. I see another hand.
It's okay.
Okay.
I think it's sort of like a follow-up from the previous question, where you're assuming that your depth map is accurate and the goal and the world around you is stationary. How would that be different if, say, you were to carry out precision landing on a goal position in a dynamic setting, say, where the goal is moving on a moving platform? Something also that ties to how you're mounting another drone on the previous drone.
Yeah, so that becomes really difficult, right? So I mean, if your world is dynamic, or if your objective is somehow dynamic, I think you need sort of a step change in complexity. So probably you need to then segment the world and try to isolate the things that are moving from not moving, so that you can then sort of take this and then say, okay, these features are attached to the stationary part of the world, and I can plan with those and so on. We have not thought about that, so I don't have like a good answer except sort of that high-level response. But certainly, for us, the world can move actually, and we're mostly robust to the world moving as long as the world moves slower than we move, right? Significantly slower than you should sort of naturally avoid it. But I think if you wanted to do something like land on the back of a truck or something that's moving, framing the problem will become a little bit more challenging, right? And especially things like this computational trick we use to take the world and partition it. You have to think very carefully about how do you think about these partitions when the partitions become time varying. And I don't have a good answer. Maybe that's not so bad, but my first instinct is that will make it very difficult, right? And certainly you can do things like, sequential convex programming, something like that will naturally take, you can bake anything into that, but it's very expensive, right? So this is cheap. This I can do in milliseconds, right? Microseconds, actually. But my instinct is that's much harder, right? The problem you're describing. Thank you all very much.